Large language models are now passing medical exams, writing specialized software, and maintaining fluid conversation. We are seeing capabilities that were previously thought to be years away. But that intelligence relies on a massive physical footprint. A standard high-performing model is constructed from hundreds of billions of individual parameters, each requiring a slice of memory and a moment of processing time. This sheer volume creates a severe bottleneck. Processing those billions of numbers makes these models incredibly expensive to train and creates noticeable latency every time they generate a single word. Currently, these systems are tethered to massive data centers. However, there is a growing demand to run this software locally, on modern laptops, on everyday smartphones, and small edge devices, without a constant connection to a server farm. To bridge that gap, engineers use a discipline called model compression. This is the science of shrinking the physical size of a neural network while attempting to preserve its reasoning ability. Hardware independence determines whether these models remain specialized research tools or become a ubiquitous utility. Without compression, the hardware requirements simply exceed what most users can afford. The first intervention targets the raw data used to build the model. This is called quantization. Most models are trained using 32-bit floating point numbers, or FP32. These high-precision decimals require 4 bytes of storage per parameter. Quantization aggressively rounds them down, converting heavy 32-bit floats into simpler 8-bit or 4-bit integers, taking a fraction of the space. It is similar to converting a high-resolution RAW photo into a JPEG. You lose a tiny amount of mathematical detail, but the file size is reduced by up to 90%. The second intervention targets the physical architecture of the network itself. This is pruning. Large models are inherently over-parameterized, containing billions of dead-weight connections that contribute almost nothing. Unstructured pruning identifies those individual weak connections and snips them away, creating a sparse model. Structured pruning goes further, removing entire anatomical units, like neurons, attention heads, or entire blocks. This structured approach is much easier for standard consumer hardware to process because GPUs are optimized to handle clean, organized blocks of data rather than a messy, scattered web. By simultaneously lowering the mathematical resolution and amputating redundant architecture, engineers can slash memory requirements while keeping the core intelligence of the system functional. The third intervention focuses on behavior rather than physical structure. This is knowledge distillation. This follows a teacher-student paradigm. A massive, high-performing teacher model is used to train a much smaller, empty student model. In this framework, the student doesn't just learn the final answer. As the teacher processes a sample, it generates a softened probability distribution, revealing its internal confidence levels. The student uses a metric called KL divergence loss to mimic that underlying thought process. By learning how the teacher weighs different possibilities, the tiny student model captures reasoning abilities, usually reserved for systems 10 times its size. Finally, engineers must solve the problem of post-compression updates. This is where low-rank adaptation, or LoRA, comes in. Traditional fine-tuning is computationally expensive because it requires updating every single parameter in the model to teach it a new task. LoRA works by freezing the original model weights, so they cannot change. Instead, it injects tiny, trainable, low-rank matrices that act as adapters. During training, only these tiny adapters are updated. This proves that we don't need to rebuild the entire brain to teach an AI a new trick. We only need to train a tiny, efficient new appendage. These 4 techniques are not isolated engineering tricks. They are stackable tools that developers combine to achieve exponential results. A prime example is QLoRA. This method marries the data-shrinking power of quantization with the efficient updates of low-rank adaptation. QLoRA allows a developer to fine-tune a massive 70 billion parameter model on a single consumer GPU instead of requiring a multi-million-dollar data center. The brute force approach of simply adding more parameters has reached its practical limit for deployment. Efficiency is now the primary metric determining how usable these models are in the real world. Model compression moves these neural networks out of the server farm and onto the hardware we already own, turning large-scale AI into a local, private, and accessible tool.